Hello and welcome to this calculus video. Today we will be talking about the mean value theorem.
Math 112.
The mean value theorem is a technical tool that allows us to rigorously prove many intuitive ideas about what the derivative of f tells you about the behavior of f itself. We will see many of these facts in future videos, but today we focus on the theorem itself. To arrive at the theorem, it is instructive to look at a special case called Rolle's theorem. Rolle's theorem says that if f is a function that is continuous on the closed interval a to b, differentiable on the open interval a to b, and additionally f of a equals f of b, then there must be a point c in a to b such that f prime of c is 0. This theorem statement is quite technical, so let's try to understand the geometry behind it. The theorem says that if f of x is a function that starts and ends at the same height across a region, and f of x is a smooth continuous line, then there must be a place where the tangent line to the graph is horizontal. I like to think of this theorem in terms of the idiom what comes up must come down. If the function f of x starts and ends at the same value, but initially goes up from x equals a, then it must come down later, and that peak will have a horizontal tangent line. Similarly, if the function starts by going down, then it must come back up, and the bottom of the valley will have a horizontal tangent line. We can phrase this in terms of the jargon that we learned in the last video. We know that f of x must have a global max and global min on the closed interval a to b, as it is continuous. If either of these extrema are obtained within the open interval a to b, then Fermat's theorem tells us that the tangent line at that point is horizontal. We know that there is a tangent line because we are assuming f of x is differentiable on the open interval a to b. If both the global extrema occur at the endpoints and f of a equals f of b, then f of x must be a constant function, as the maximum and minimum value of f of x are the same. Therefore, every point in between has a horizontal tangent line. Now we are going to generalize Rolle's theorem to the mean value theorem. The mean value theorem says that if f is a function that is continuous on the closed interval a to b and differentiable on the open interval a to b, then there is a point c in the open interval a to b such that f prime of c equals f of b minus f of a over b minus a. The mean value theorem looks scary because the conclusion is complicated, but it is easier to understand if we note that f of b minus f of a over b minus a is the slope of the secant line to f of x at x equals a and x equals b. So then the mean value theorem tells us that as long as f of x satisfies the hypotheses of the theorem, then there is always a place x equals c between a and b where the tangent line at c is parallel to the secant line through a and b. As we can see from the graphs, this seems plausible for nice smooth functions. Another interpretation of the mean value theorem that seems to help people's understanding is that it says that there is a place in the interval where the instantaneous rate of change equals the average rate of change over the interval. I won't prove the mean value theorem in detail here, but I will tell you how to do it if you are interested. The trick is to apply Rolle's theorem to a new function h that is defined to be the difference between f of x and the function whose graph is the secant line through x equals a and x equals b. That's all for now, folks. Today we stated Rolle's theorem and the mean value theorem that are both results that we interpret as saying that if f of x is a smooth enough function, then there is a place where the instantaneous rate of change equals the average rate of change over a region.
Math 112.